Hi everyone. Just addressing your feedback from today. On the quiz, the last question, which direction did the reaction shift? So in the last reaction, the reaction was endothermic, and we were increasing the temperature, and for endothermic reactions, an increase in temperature drives it towards the products, towards the right. And again, if you wanted a complete explanation of that, I would say watch the video I posted about temperature dependence of equilibrium constants, because it has to do with reaction rates and relative activation barriers. But a quick and dirty way to predict, not explain, but to predict that is to say, okay, let's say I had some reaction where I go from A to B. It's endothermic, so we think of heat as being like a reactant. And if I increase the temperature, that is like increasing the concentration with increasing the amount of heat, so that shifts the reaction to the right. Again, that is not how you actually explain it. That's just a quick way to predict whether raising the temperature will shift a reaction to the left or right, depending on if it's endothermic or if it were exothermic. Okay, so there's a couple questions here about the last part I was doing in lecture, where I was making some approximations about the value of X, the amount that the reaction concentrations decrease by. And your question was, can we just use the quadratic formula and not make assumptions? Would that be acceptable on a test? Yeah, you do not need to make those assumptions. You don't need to make the approximation that I made. And yeah, if you want to do the full calculation explicitly with the quadratic formula, that is perfectly fine, except in cases where you can't do that. Let me explain. A case like this, where I was going from, say, A breaks into B plus 2 times C. And let's say I was starting with, initially, I'm making up numbers again. 1 mole of this, no moles of that, no moles of this. This one is going to, well, the reaction will shift towards the product, so I will lose some A, I will generate some X, and I will, just some B, and I will generate twice as much C. So my equilibrium concentration should be 1 minus X, X, and 2X. So when I plug these equilibrium concentrations into my law of mass action, I have products to their coefficients over reactants. So I have X times 2X squared over 1 minus X. This will end up being 4x cubed over 1 minus x. And that you can't solve exactly with either the quadratic formula or any other. I mean, there are other formulas. One reason why you can't use the quadratic formula is that is not a quadratic equation. That is a cubic equation. It goes as the cube of x. So you can't use the same form of the quadratic formula. It doesn't apply in this case. There is a comparable equation, a comparable formula for finding the cube roots of cubic equations, but it's big, messy, long, and not worth our time. But one thing we can do, so point being, this is an example where you can't make that assumption, where you can't use the quadratic formula, and you're kind of at a loss unless you make some assumptions. So if, again, this is important, if k is small, much, much less than 1, very, very, very small, then I don't expect the reaction to shift much towards the products, meaning that I expect x to be small. And then if x is small, then I can make this approximation. I can say this should be equal to approximately 4x cubed over 1. 1 minus something very, very small is still approximately equal to 1. And this is more doable. I can multiply k by 1, divide by 4, and then take the cube root. Just your calculators, most scientific calculators have the ability to take the cubic root of a single equation. So that should be solvable at that point. So in that last, so there are another comment about this. That on the last concept we discussed, were you making an educated guess based on the value of k? Since k is much less than 1, it's basically equal to 0. So I would say you're not making an educated guess. You are making an educated approximation or an educated assumption. It's an assumption that because k is small, x is small. So when you say it's basically equal to 0, I'm assuming you are referring to x as it. We don't assume necessarily that k is equal to 0. We assume that x is very close to 0. So 1 minus something is very close to, 1 minus something very small is approximately equal to 1. So yeah, I would say it's not so much an educated guess, it's an educated approximation. Why would it be helpful to find x if it's almost 0? Well, it's not so much that we want to figure out the equilibrium concentrations. In this particular example, we were trying to figure out what equilibrium concentrations were. And to do that, we know that they need to be approximately equal to how much the reaction shifts. The reaction shifts, you lose some A and you produce some B and C. And we want to know how much B and C do we produce. That amount won't be 0. It is not negligible. If that were the case, then I would assume, yeah, you have no B and no C, and then the problem will be done. And that's not exactly, the point is that that's not accurate. Some B and some C is produced. What is interesting is that you're looking at the difference between 1 and x. If x is very small, here's an important approximation. Here's where the approximation comes in. 1 minus a small number is approximately equal to 1. Each of these expressions is like 0 plus x. And that is going to be approximately equal to x. Any number is infinitely larger than 0. So this is not an approximation. You shouldn't say this is approximately equal to 0. You should say 0 plus x is approximately equal to x. And in fact, it's exactly equal to x. 1 minus x, if x is small, is approximately equal to 1. So that's essentially how we're doing that approximation, or why you don't just completely neglect x in the numerator, but you can neglect it in the denominator. When do you use an ICE table? Do you use it to find K and equilibrium concentrations? For the most part, that's how it's used, or rather how they're used. And you know, there will be times when you're asked to find an equilibrium constant, but you don't need to use an ICE table to do it. So I could say, here's an example of a question. It's a straightforward application question where I tell you these are the equilibrium concentrations of products and reactants. They have these values. What's the equilibrium constant? And that one is straightforward enough. You simply plug in those equilibrium concentrations into the law of mass action and calculate K. So that one's pretty straightforward. Anything else you'll probably want to use an ICE table for. Anytime you are dealing with a pre-equilibrium condition and a post-equilibrium condition, like the questions we started with today. You started with a certain amount of reactant, you end with a certain amount of products and reactants. So that is a pre-equilibrium condition and a post-equilibrium condition. Before you were started, when you started, before you reached equilibrium, and after, once you had reached equilibrium. So why would you use an ICE table for that? Again, ICE table stands for initial change equilibrium. It's describing a passage of time, how a process that has occurred. So anytime you have a problem that is dealing with before equilibrium and post-equilibrium, you'll end up using an ICE table for that. Those were all the questions that I had that were of pointed note. I had a few people make comments that they liked the quiz and that we went over the answers immediately and that it wasn't graded. And then I think then it's useful as an assessment and not an examination. It's just a quick chance to self-assess how we're dealing with the material. So I'll probably continue doing those sporadically throughout the rest of the course. Yeah, and that's it. I'm going to post another secondary video dealing with a few more examples of using ICE tables to do calculations. And so yeah, look to see that in a little bit. Have a good day, everybody. I'll see you on Friday.